So now let us look at the projective geometry and transformation in the 3D space after we have looked at the SE3 transformation for rigid body motions. And many properties of the entities in the projective 3 space are actually straightforward generalization of those in the projective 2D space. An example here is that we'll see in a few slides time that the homogeneous coordinates of a point in the P3 space, Euclidean space, is actually simply augmented with an extra dimension in the P2 space. An example here is that in the P2 space, let's say X is in the projective 2 space, then this would be X1, X2, and 1 here. So in the P3 space, in the P3 space here would be simply the augmentation of X1, X2 with the third dimension and 1 here to represent this. So it was a straightforward extension of this. Nonetheless, additional properties may appear by the virtue of the extra dimension. An example here would be two lines always intersect on a projective plane. So as long as it's on the plane, they will always intersect at a certain point. Even at infinity, they are going to intersect at the infinite point, as what we have seen in the previous lecture. But in the 3D space, they did not necessarily intersect. So in the 3D space, even though the lines might not be parallel, they might not necessarily intersect. So this line here could be under this line in the z-axis, according to the z-axis, and they might not intersect at all. And let us first define the how to describe a point in the projective 3 space. As I've mentioned earlier, that this would be a 4 vector given by x1, x2, x3, and x4, where the scale doesn't matter. So this we can convert the homogeneous representation here with a 4 vector into an inhomogeneous one by simply dividing by x4, the last element of this homogeneous coordinates. So this property is the same as what we have seen in the P2 space for a representation of the points, where it's simply x1, x2, and x3 in the P2 space, and we'll simply take x1 divided by x3 and x2 divided by x3 to convert it into the inhomogeneous coordinate. And homogeneous point with the last element to be equals to 0 represents the point at infinity. So this would be x1, x2, x3, and 0. And it's analogous to the P2 space, where at the point at infinity, where the last element here would be equals to 0. So we simply extrapolate this thought by adding one more dimension to the homogeneous representation. And the projective transformation acting on the P3 space is a linear transformation on X by a non-singular 4x4 matrix. So this definition here is also a direct extension of the transformation, the linear transformation on the P2 space, as what we have seen in the previous lecture. X prime here will be given by X multiplied by h multiplied by x, where h here is a 3x3 matrix, the x and on a 3x1 homogeneous coordinate. So here h will become 4x4. This is a direct extension of this P2 space linear transformation. This would be a 4x4 matrix, and the x over here would be a 4x1 vector that represents the homogeneous coordinates of a point in the projective 3 space. And here the metric h is homogeneous and has 15 degrees of freedom. Altogether, it's 4x4, so there are 16 elements in this H metric and less 1 for scaling. This is similar property as the homogeneous transformation or the linear transformation of H in the P2 space. And as in the P2 space, the mat is a collineation. That means that in the 3D space here, if I have any line or I have any points that are collinear that forms a line, after mapping each one of the points by h over here, it's going to form it's also going to sit in a line, be collinear in a line. This preserves the incidence relation of such as the intersection of a point or with a line, or a line with a plane in the order of contact. And uh, the we'll also define the plane in the 3D space. So this is an entity that doesn't exist in the 2D space, because everything is actually projected onto the plane in the 2D space, in the projective 2D space. But in the projective 3D space, this would become an entity itself. And a plane in the projective 3D space may be written in this form here as this polynomial equation over here, where the coefficient pi 1, pi 2, pi 3, and pi 4, and the x, y, z coordinates over here. And homogeneizing this would simply be dividing x by x1 over x4 and y x2 over x4, and then z x2 x3 over x4. By substituting these three terms here into this equation here, this is what we will get here in the homogeneous coordinate form. And we can factorize this by putting pi 1 to pi 4 here into the vector here, and then we will get this homogeneous equation over here, the dot product of this pi of the plane multiplied by the point x would be equals to 0. And this expresses the point is in the plane or on the plane when the dot product of these two is equals to 0. Hence, this is similar to the line point dot product in the P2 space here. This is analogous. Hence, we can see that since the dot product of the line and the point tells us the duality constraint or the duality principle of the line and the point, we can also see that these two are interchangeable. Hence, plane and points are dual in the 3D space. And we can define that only three independent ratios of this pi 1, pi 2, pi 3, and pi 4 of the plane coefficients are significant. Therefore, a plane has 3 degrees of freedom in the 3D space. And the first three components of pi corresponds to the plane normal. This means that pi 1, pi 2, pi 3, it makes up the vector, the normal vector of this particular plane here. And using the inhomogeneous notation, which we have seen earlier, that it's a pi 1 x plus pi 2 y plus pi 3 z plus pi 4 equals to 0. So this inhomogeneous notation, the first three over here can be factorized into this form here, where x is xyz and x4 is 1, and then d here is equals to pi 4 in this formulation over here. So this the first term over here would be the normal vector, and the last term here can be used, d here can be used to form the distance of a plane from the origin. So here, let's say my origin, the reference plane point is here. So this would give me the normal vector, that is the distance between the uh, origin and the normal formed by this plane over here, and this is given by d divided by the normal vector, the norm of the normal vector. And under the point transformation of x prime equals to h multiplied by x, the plane transformed in this way. The plane of pi prime is equals to h inverse transpose multiplied by pi. So I won't derive this, but I'll leave this derivation to you to prove. Basically, we can make use of the relation of pi transpose x equals to 0 to prove this. And in the projective 3D space, there are numerous geometrical relations between the planes, points, and lines. So a plane is defined uniquely by the join of three points that are not collinear. So any 3 points in the 3D space will always define a plane. And all the joint of a line and a point, they are not incident. So if I have a line and a plane, they are not incidents on each other, I can use these two to define a plane. We'll see in more detail later on. And two distinctive planes always intersect at a unique line. So this is analogous of a line on the 2D projective plane that you always intersect at a point. And three distinctive planes will intersect at a unique point. So we'll see the explanation for all these 3 points later. And so first, let us look at the definition of 3 points defining a plane. Suppose that we have 3 points x1, x2, x3, or generally denoted by xi, and they are incident with the plane pi. This means that the 3 points are sitting on the plane. In any case, any 3 points that are sitting on the plane are definitely not going to be collinear and vice versa. So if they are not collinear, they will also imply that it's always going to form a plane, where each point here would satisfy this point plane equation over here, the incidence relation between the point and plane equals to 0 for I equals to 1, 2, and 3. And stacking all of them together, this would be the 3 points together. This would be the equation that I will get. So if you take this out, you'll get 3 equation here. X1 transpose pi equals to 0, x2 transpose pi equals to 0, and x3 transpose of pi equals to 0 here. And stacking them all, this is the relation that we will get. And the 3 by 4 matrix of this has a rank of 3 when the points are in the general position. This means that they are linearly independent. I would have 3 unique constraints here. Hence, this matrix would have full rank over here. And the plane pi defined by the points is obtained uniquely up to scale as the one-dimensional right null space. Since this is equals to 0, this is equivalent to a homogeneous linear equation. It's a 3 by 4 matrix by a 4 multiplied by a 4 by 1 vector equals to 0. So this is equivalent to the famous equation in linear algebra, the homogeneous linear equation of ax equals to 0. So to solve for x here in the null space, I need to solve for the null space of A as the right null space of A, and this can be uniquely obtained since it has a rank of 3. And in the case where this 3 by 4 matrix here has a rank of only 2, this means that points are linearly dependent on each other. Then the null space would be two-dimensional. The null space of x1, x2, and x3 multiplied by pi equals to 0 would have a null space of 2 dimension. Then this means that the points are collinear. This means that all these 3 points here, they form a single line, and hence they are dependent on each other. And this defines a pencil of planes with the line of collinear points as an axis. So since all these 3 points must lie on the plane, any plane, and we can see that the plane can actually rotate around this particular line. So any plane that is on this pencil of planes rotating around this line over here would contain these 3 planes would contain these 3 points in the plane, and hence this is a rank division configuration, and where the null space is only 2-dimensional. And the second property that we talk about is that 3 planes will define a point. So in the case where the rank of A here is this guy here is equals to 3, then this means that all the 3 planes are unique and they intersect at a certain unique point over here. And in the case where it's rank division, it's equals to 2, the rank is equals to 2, then we can see that these are the 4 configurations that might be happening. So it means that there's no unique point of intersection, but they are likely to intersect at either a line or a pair of lines or 3 lines over here. And then there's also the configuration where the rank equals to 1, where the plane are simply parallel to each other. And in the case where the rank of A equals to 3, we can see that 3 planes intersect at a unique point of here given by x over here. So what it means is that this point here will be sitting on all the 3 planes, and this would define the point plane duality principle. And the points on the plane X may be written as this equation over here, where X here is the point that is in the plane of pi. So here I'm defining a point denoted by a capital X here, and this can be denoted as the linear combination of M, a M matrix, a 4 by 3 matrix over here, multiplied by a vector. So in this case here, we can see that this 4 by 3 matrix is a of M. So this matrix of M multiplied by x1, x2, and x3, it becomes a linear combination. So this means that if I have a vector of m1 and then a vector of m2 and a vector of m3, so this is a 4 by 3. This means that each one of these m is actually a 4 by 1 vector. I would end up to the multiplication of this, which is x over here, would be simply a linear combination of m1 plus m2 plus x3 multiplied by m3 over here, and this is going to give me my point of x over here. And linear combination of m, this means that m is defining the whole subspace within the plane. Any point within the plane is going to be a linear combination of any three of the this basis vector of m1, m2, and m3 over here, and they are going to form a linear subspace in the in the space of subspace of pi. And since the linear combination of M is in the subspace of pi, this means that the dot product of this the basis of M here is going to still be living in the subspace of pi here. Hence, the dot product of pi with M is always going to be 0, because this means that the M over here, intuitively or geometrically, since M over here is the linear combination of M, is going to give a point that lives in the plane, on the plane. A point plane relation, incidence relation, will tell us that the dot product of the plane and the point is going to be equals to 0. Hence, x here is just a coefficient, or is just a linear coefficient that tells us the linear combination of M to be in the any point in the plane over here. And M here is not unique. Suppose that the plane is given by the 4 by 1 vector here, A, B, C, D, and A is non-zero, then M can be simply written as this form over here, where P is given by this guy. So I'll leave it to you to prove that, to just simply substitute this pi over here and transpose multiply by M to show that this is indeed equals to 0 over here. And this is M transpose equals to this is indeed a solution to this and this. Now, after looking at the definition of the plane in the projective 3 space, let's look at the line definition in the projective 3 space. A line is defined by the joint of 2 points or the intersection of 2 planes. So in this case here, we can see that the line is here, defined by the intersection of any 2 planes, or it can be defined by the joint of any 2 points over here. And line have 4 degrees of freedom in the 3D space. So a general sketch of proof would be why it has 4 degrees of freedom is that we can see that after we fix this plane over here, this line here that is defined by the intersection, the 2 planes over here can be defined by 2 points on this line over here. And these 2 points, each one of these would have 2 degrees of freedom on the plane. It can move anywhere x, y direction in the 2 planes. And this will also move x, y direction. Hence 2 plus 2 will give us 2 degrees of freedom. We can also think of this as the 2 points here on the projective plane over here. So in this case here, this could also move x, y, and this could also move x, y, and hence the line has 4 degrees of freedom. But it's awkward to represent the 3 space line with a homogeneous 5 vector since it has 4 degrees of freedom. So we'll look at 2 alternative representations here instead of representing a line with 5 vectors here. Suppose A and B are two non-incidence space points in the 3D space. The line joining these 2 points is represented by the span of the row space of the 2 by 4 matrix W composed of A transpose and B transpose as this. So the span of the row space, the span of this guy over here, A and B here, would give us the points that are joining that there are lies on this particular line here. And we can see that the span of W transpose here is indeed given by the linear combination of A and B. So since A and B here are 2 points on the line, any linear combination of these two is going to give us any point on this particular line as well, since the direction of A and B is pointing towards is aligned with this line. So any linear combination is going to be in the subspace of the line, and hence the span of W transpose is going to give us a pencil of points on the line. And the span of the two-dimensional right now space of W is the pencil of planes with the line as the axis. And what this means is that mu and A over here, let's denote this as A prime and another point A prime and another point B prime. So this is like we are moving along this line here by a certain magnitude, by a certain scale of mu over here, and we are moving along this line by a certain scale of alpha over here. So it becomes A prime and B prime, and the span of these two, A prime and B prime, is still going to be equal to the span of A and B over here. Hence, they are going to define the same line. So what this means is that suppose we have a plane P and another plane Q over here, which is the basis of the for the null vector of this W, that is representing the line over here. Then we would have W multiplied by P would be equals to 0, since P is in the null space of W, and that would be equals to 0. Similarly, W multiplied by Q here is also going to be 0, since Q is also in the null space of P, and consequently we would have A transpose P equals to 0 and B transpose P equals to 0, given by the definition of this guy here. So multiplying this would be equals to 0, and multiplying this would also be equals to 0, given by this guy here. So that the plane is P is actually a plane that containing both the point A and B, since by this equation here shows the incidence relation of the A and the plane P as well as B and the plane P here. Similarly, Q is also a distinctive plane, since this must hold true, as well as A transpose of Q must be equals to B transpose of Q equals to 0, since Q is also a basis in the null space of W. And that means that Q is a distinctive plane also containing both A and B, given by the plane point incidence relationship over here. And hence, A and B here must lie on both of the planes P and Q, since it fulfills this incidence relation for P as well as for Q. Hence, it must be lying on both the plane P and Q. And so the line here defined by W here, which contains A and B, these 2 points of A and B, must lie at the plane intersection. Hence, it defines this particular line over here. And any plane of the pencil with the line axis is given by the span of the two planes of P and Q. This means that any linear combination of the two planes will be giving us another plane that is intersecting the two planes P and Q here at the line of A and B. And the dual representation of the line as the intersection of two planes P and Q follows in the similar manner. So we can define W star transpose as the dual previously we defined W as A transpose and B transpose as the span over 2 points A and B. Now we are defining this as the intersection of the two planes P and Q in the similar manner, which we call W transpose here. And this dual representation has the property that the span of W transpose is the tensor of planes of P and Q. So this is directly following the duality principle where W here defined by A transpose and B transpose 2 points. It's given by the span of these two A and B here. So it's lambda plus A plus mu of B to be any point on this particular line defined by the 2 points over here. And the span of the two-dimensional null space of W is the tensor of points on the line. So this also directly is a duality of the span of the two-dimensional null space of W uh, defined by the 2 point is the tensor of planes on the line. So this shows that there is a duality principle between point and planes. And the two representations are represented by W star W transpose equals to W multiplied by W star transpose equals to 0. Since the point should lie on the line. So this actually gives rise to A transpose of P equals to B transpose of P equals to 0, since A and B should lie on the plane, and as well as uh, B A transpose of Q plus B transpose of Q should be equals to 0 as well. Now we can also see that the joint and incidence relation can also be computed from the null spaces. The plane of pi defined by the joint of a point x and line w. So I have a line here which I denote as w, and a point that are not coincident with each other. This means that the point doesn't lie on the line. Then I can use the line and this point w and x here to define the plane of pi over here, and this is given by the null space of the uh, of this matrix over here defined by w and x prime over here, which is obtained by the null space of this guy. This particular relation here can be easily proven here, where since we define w over here as any 2 points, the span of any 2 points which we call A and B. This means that M over here is actually equals to A transpose, B transpose, and X transpose, defined by these 3 points, A, B, and X. And therefore, these 3 points transpose, AB transpose and X transpose multiplied by pi should give us 0, since these 3 points are lying on the plane itself. And the duality of this also holds. This means that I have a plane defined by pi transpose as well as W here. W here is defined by two planes, which we define this to be W star that is equals to uh, P transpose Q transpose as well as pi transpose here. And then if we put it into multiply by point X, which has to be lying on all the three planes. So since this line is defined by a pencil of planes, this means that the point would have to define by PQ, and it will have to need to sit on PQ as well as pi. Hence, the dot product of this P transpose, Q transpose, and pi transpose multiplied by X is going to be 0. Now let us look at the second way of representing line, which we call the Plucker line coordinate. And the Plucker line coordinates are the 6.0 vector. It's a 6 by 1 vector represented by L over here, where the first three element is the direction of the line. Suppose that we have a line that is spanned by A and B, 2 points of A and B over here, and we will first compute the direction of this. It's directly given by B minus A, and that would be the three-dimensional vector that occupies the first three elements of the Plucker line. And the second, the set of the Plucker coordinate, or which is the last three coordinates of the Plucker coordinate, is simply given by the cross product of these 2 points. So this is the equivalent to the moment vector that is given by the vector A and B over here, and the cross product of this, so, and the directional vector of this, and this will form the Plucker line coordinate. We'll see more of this Plucker line coordinates representation, the usage of this Plucker line coordinate representation when we look at the generalized camera, where it's a non-central projection camera in the later lectures. And now suppose that we have two lines, L and L hats, are the joints of the points A, B, as well as A and B hat, respectively. Then the lines intersect if and only if. So I have 2 points here, two lines here, uh, which is represented by A and B, and then A hat and B hat, two respective lines here. And then the two lines will intersect if the 4 points are coplanar. This means that they all lie on a plane. This means that these two lines would become coplanar as well. Hence, it's equivalent to 2D, the projective 2D space, where the two lines will always intersect at a certain point. And to check this, we can see that the determinant needs to be of this A, B, and A hat and B hat needs to be equals to 0 of the matrix that's formed by these 4 points over here, needs to be equals to 0, and we can see that the proof here would be simply the determinant here is given by this the sum of these two dot products over here, and we can I will skip the full derivation over here, but if you wish, you can actually prove this for yourself by working out, substituting this A, B, and A hat and B hat with the full vector form, and then computing out the determinant. So we will be able to see that this is indeed equals to this guy over here, and can be evaluated into this form over here, which is given by this guy over here, which needs to be equals to 0, since the dot product of this uh, since the dot product of the final moment vector over here, this guy over here, uh, M and M uh, hat, it's representing the moment vector in the Plucker line of AB and A and B, A hat and B hat over here. They must be in the same direction since they are coplanar. They are lying on the same plane, and the dot product of these two is going to be equivalent to the determinant of this guy over here, and that is going to be 0. And other properties here is that which can be directly derived from the duality principle of a point and plane. Now suppose that two lines are intersection, then of the planes PQ and as well as P hat and Q hat here, defined by PQ and P hat and Q hat here, then the determinant of this needs to be equals to 0 if and only if the line intersect. So this determinant here can be directly extended from the proof here, can be directly extended from the previous proof of line, of a point that defines the line. So previously it's A, B, and A hat, B hat over here. And since there's a duality between point and plane, that means that this should also hold. This to replace the points with planes, it should also hold as long as the line defined by PQ and P hat and Q hat intersects. And similarly, if the line L intersects is an intersection of any two planes, and L hat is the joint of any 2 points, then this relation should also hold, since there is a duality. That means that I can simply replace one of this set with points and the other one with as still remain as a plane. Now, finally, let's look at the definition of quadrics and dual quadrics. So a quadric is a surface in the projective 3 space defined by the equation here. So this is similar to the equation of conics that we have seen in the previous lecture, except for now, instead of this being 3 by 3 and this being 3 by 1, we have a 4 by 4 matrix, and this is a 4 by 1 vector. Now Q will have the same or similar properties as the conic C that we have seen in the previous lecture, and it will not and often the metric Q and the quadric surface it defines are not distinguished. We'll simply refer to Q as the quadric instead of a quadric surface. So as mentioned earlier on that the quadric follows the same property directly from the conics, and we have seen in the previous lecture that a conic is a 3 by 3 matrix with 5 degrees of freedom. That's because it's a symmetrical matrix with 6 unique elements and minus 1 for the scale. It is left with 5 degrees of freedom. And in the case of a quadric, it's a 4 by 4 symmetrical matrix. This means that it has 10 unique entries minus 1 degree for scale, and therefore it's left with 9 degrees of freedom. And as a result, 9 points in general are sufficient to define a quadric. And if the metric Q is singular, then the quadric is degenerate and it may be defined by fewer points. So this is a direct extension of the properties of a conic. We saw that if the conic is degenerate, that means that the rank of C here is lesser than 3. Then it could be defined by a repeated line or two lines that are in that lies on the inverted cone, and this can be defined by fewer points instead of 5 points. The C here, the conic can be defined by only 2 points or 4 points over here, and this is the same case here. If Q is singular, then it can be defined by fewer points. And the intersection of a plane pi with a quadric is a conic. So we can see that this is a quadric surface defined as Q, and the intersection with a plane over here would give us this contour here, which is exactly the intersection on a conic section. And recall that the coordinate system for the plane can be defined as the complement space given by this guy here, and or pi is the right now space of M here, and then the X here is a linear coefficient or linear combination of the M that gives any point that lies on pi, as we have seen earlier. Therefore, points on the plane pi are on the quadric if it fulfills this equation equals to 0, which we have seen earlier, that we can directly substitute this x, which is the point on any point on this plane pi over here. Uh, and as with this particular equation, x equals to m small x over here. So we will get this equation over here, and as a result, we can see that the small x over here is the coefficient, and we can group together is the linear coefficient of the linear combination of m such that it forms the point on the plane over here as we have defined in the previous slides. And here we can directly group this m transpose qm together and call it C. So we can also define this guy here, since this is a 4 by 3 and this x here is a 3 by 1 vector. So this means that this becomes 3 by 1 and this becomes 3 by 3 because this is 4 by 3, and Q is 4 by 4. M transpose will become 3 by 4. So as a result, this becomes 3 by 3. So we can collectively call them, group them together and call this C. And we can see that C here, or this particular equation here, would become the incidence relation for a point to lie on a conics. Hence, the intersection of the plane pi would be, or with a quadric, would define the conic section here. So under the point transformation x prime equals to hx, a quadric transform as q prime equals to h inverse transpose q h inverse. And this can be easily proven that if I have a point or x prime transpose q of prime x prime equals to 0 here, then this transformation here can be rewritten as x transpose h transpose, which gives me x prime transpose, multiplied by q prime multiplied by h of x equals to 0 here. Hence, we can collectively call this guy here as q to get the equation of x transpose. Q multiplied by x equals to 0. Therefore, q would be equals to h transpose q prime h, and by moving the h across to make q the subject, we will get this relation over here. The dual of a quadric is also a quadric. So dual quadric are equations on the plane instead of defining it over a point here, since there is a duality between point and plane. So defining this equation here means that this quadric here is defined by a point x, but we can also define this in terms of the duality of a point plane duality. Hence, we will get the dual of the quadric defined by q star over here, and q star is the adjoint of q, or q inverse if q is invertible. So adjoint is defined by this, where the adjoint of A is simply C transpose, where C is the cofactor of A, given by this definition over here. And under the point transformation of H prime equals to Hx, a quadric or dual quadric transforms as this, and I'll leave it to you to prove it. And the proof would be simply done by the same way as shown here. Here's some common quadric surface: the ellipsoid and the hyperboloid on one sheet, and this is given by these plots over here. There's also hyperboloid on two sheets, as well as the elliptic cones that is given by this. This is a degenerate quadric where the rank is only equals to 1. And there's also a full rank elliptic paraboloid, as well as the hyperbolic paraboloid. So the hierarchy of transformation is also a direct extension of the P2 space for the P3 space. Instead of a 3 by 3 transformation matrix, we would have a 4 by 4 transformation matrix. And the highest level of the hierarchy of transformation is the projective transformation, where there's a 15 degrees of freedom. That means that every entry here is unique, minus 1 for the scale, and it can be represented in the same form of A, T, V transpose and small v here, where now A is a 3 by 3 matrix and T is a 3 by 1 vector. So there are invariance properties such as the intersection and tangency of surfaces in contact, as well as the affine transformation here, where this is also a direct extension of the 2D projective geometry, where now we have we can represent this affine transformation as AT0 and 1, where the last row here is going to be 0 and 1. Similarly, we also have a similarity transformation, which is 7 degrees of freedom. So now this rotation matrix and the translation vector is what we have learned earlier on, that lies in the SE3 space. So this rotation matrix now is in the SO3 space, and translation vector is in the 3 Euclidean space, and the Euclidean 6 degree of freedom rotation. So this is equivalent to the rigid body motion or the rigid body transformation that we have learned at the start of this lecture. Now, in summary, we have looked at how to explain the concepts of SE3 group and use it to describe the rigid body motion in 3D space. And we also have looked at how to represent points, planes, and in the projective 3 space, and describe the point plane duality. Then we look at how to describe a line in the P3 space using two representation, the null space and the span metric, as well as the Plucker coordinates. And finally, we extend the P2 conics property into the quadric. Thank you.